Chapter 10, Electrostatic. So, learning outcomes. Understand how to use Coulomb's law and the superposition principle. Determine the electric field due to known quantum charges within the surrounding vicinity. Topic outline is electric charges and force, Coulomb's law, electric field. So let's first talk about history. So the history of electric charge is 600 people common era which first discovered and attractive properties of amber and rock. 1680 electric bodies referred as well as track. 1725 AD, Dufay found the distinct two types of electricity. 1750 AD, Franklin learned about the positive and negative charge. 1770 AD, Coulomb created the inverse square law. 1890 AD, J.J. Thomson created the quantization of electric charge electrons. So what is electrostatic? Electrostatic is the study of electromagnetic phenomena that occur when there are no moving charges, example statically breathing has been established. Electrostatic. Branch of a physics that deals with the electric effects of static charge. Electrostatic forces are attractive or repulsive forces between particles that are caused by their electric charges. Electric charges flow through a conductor, insulator of a material where electric charges do not move easily, and electroscope is a device to use to detect the charge. So charges, so this is an atom, and the color green is a proton, which has a positive charge. The red one is the electron, which has a negative charge, and yellow is the no charge, which is neutral. So electric charge. Recall that fundamental principle carries something called electric charge. Protons have exactly 1 unit of positive charge and electrons also the same with a unit of negative charge. Electromagnetic force is one of the basic instructions in nature, like charges experience opposite forces. Opposite charges attract to each other magnetically. Electrical current is a flow charge. So charge balance. Neutral atoms are made up of equal quantities of positive and negative charges. Neutral carbon has 6 protons, 6 electrons, and neutrons. Electron can be stripped off of atoms. Electron occupy the golden ball outskirts of atoms. Usually, charge flow in such a way to maintain neutrality. Excess positive charges attract excessive negative charge. Your body has 5 times 10 to the power of 28 positive charge and 5 times 10 to the power of 58 negative charges balanced within million or billion. Charge separation. You can separate charges by rubbing feet or carpet, atmosphere of course ground, silk on glass, balloon and gel. Insulator keep charges where they are not flow. Conductor distribute charge equally on surface. Charge is free to move about the province. Why do the charge collect on the surface? So here's the properties of charge. Opposite charges attract while the same charges repel. So properties of charges, conservation of charge. In a isolated system, sum of total charge remain constant whatever changes takes place in that system. While quantization of charge, the charge of a particle or a body is always an integral multiple of fundamental of electron charges. The properties of charges always associated with mass. Charge is relatively invariant. Charge system unit is coulomb. A charge at rest reduces only electric field around itself. A charge moving with uniform velocity creates both electric and magnetic field. And take note that charge can exist without mass, or mass can exist without or within charge. So electrostatic. In conducting material, the outer electrons of the atom are loosely bound and free to move through the material. So, conductor transmit charges readily. Next is semiconductor, which is between conductor and insulator. And semiconductor are intermediate. Their conductivity depends on impurities and can be manipulated by external voltages. While insulators are, in short, doesn't transmit charges at all. So here's an example for this electric charge, the transfer of charge. Here we're gonna use a glass rod and silk because this material can attract electrons more than others. The glass rod is rubbed against silk. Electrons are pulled off the glass into and usually matter is changed. Matter is charged neutral because the number of electrons and protons are equal. So as you can see, when the negative charge added in the silk, a positive charge or a proton added also on the glass rod. So there is 5 electrons and there is also 5 protons on the glass rod. So glass and silk are insulators, charge stuck on them. So next is method of charging the body. So friction, conduction, induction, thermodynamic emission, kinetic electric, and kinetic. So let's talk about friction. When insulator is rubbed together, one gains of electron and become positively charged, while the other gains electron and become negatively charged. So this is an example. So see, once there is some reaction when the balloon was rubbed in the air and the other became positive and the other became negative. Conduction. When a charged conductor makes contact with a neutral conductor, there is a transfer of charge. So the circle is a what do you call this? Neutral, and the rod is negatively charged. So when it touched, it became negative too. Then next, the again the ball is neutral. Then there's a rod is positively charged. The proton is transferred to the ball, leaving both them positive charge. So next, induction. Bring a negative charge rod near the conducting sphere. Connect the sphere to ground through a conducting wire from this side where negative charges appear. Due to ground, the negative charge flows to the ground, leaving the sphere positively charged. Now, remove the rod. The positive charge on the sphere arranged starting from it. So this is a step on how to do induction. So first, it's just that bring the negative charge near the rod. So put the rod in the sphere. Then as you can see, they call this, they are supposed to, it attracted the positive charge because the rod is negative, and the negative charge had been repelled because it's same charges. So we put a rod, and then after that they arrange themselves uniformly. Electron. So next is electroscope. Electroscope is a device which detects any charge on an object. So Coulomb's law, the electric force between two charges is proportional to the product of the charges, inversely proportional to the distance between them. So Coulomb's law, so is a medium. You can see suddenly away because it has another charge which is opposite charge, that's why it repels. That's when they learn about the electric charges. So charge is quantized. K is equal to multiple of elements and charge V, E is equal to 1.6 times 10 to the power of negative 10 coulombs. Electron ng its charge is negative E, mass is 1, diameter is 0. Proton is plus E, and the mass is 1,836, and its diameter is negative 10 to the power of negative 15 m. Neutron is 0. Its mass is 1,839, and the same as the proton. Then positron is positive E. Its mass is 1, and diameter is 0. So protons and electrons are made up of quarks whose charge is quantized as multiple of E over 3. Quarks can be isolated. So this we call them law holds between two particles in a medium. F21 is equal to F12 is equal to K Q1 Q2 over R squared. So F21 is the force on particle 2 due to 1. Then F is equal to force on particle 1 due to 1. Due to 2, sorry. R is equal to distance between 1 and 2. K distance between 1 and 2. So next we use in the vector form F21 and F12 is equal to K Q1 Q2 all over 3, R squared, where R is the unit vector in the increasing direction of R. Coulomb's law valid for point charges only, K is minus 1 over 2, where is the permitted medium. So this is the permittive of free space. ER is equal to relative permittive medium, also known as the dielectric constant of the medium. ER is equal to 1 for free space, and ER is equal to infinity for conductors. So Coulomb's law is a conservative force. It is a central force since it's central. Hence, in the absence of the external force, angular momentum of one particle with respect to the other is conserved. So next is the superposition principle. This calculation demonstrates an important property of the electromagnetic field known as the superposition principle. According to this principle, a field that arises from a number of sources is determined by adding an individual field from each source. The principle in which an electric field arises from several sources are determined by the superposition of the fields from each of the sources. In this case, the electric field as a location of Q1 is the sum of the field due to Q2 and Q3. Studies of electric fields over an extremely wide range of magnitudes have established the validity of the superposition principle. The vector nature of an electric field produced by a set of charges is produced by a significant complexity. Specifying the field at each point in space requires giving both the magnitude and the direction of each location. In the Cartesian coordinate system, this necessitates knowing the magnitude of the x, y, and z components of the electric field at each point in space. It would be much simpler if the value of the electric field vector at any point in space could be derived from the scalar function with magnitude and sign. So, principle of superposition for Coulomb's force. Electrostatic force is a two-body interaction electrical force between two point charges is independent of presence or absence of other charges, and so the principle of superposition is valid. Thus, force on charged particles due to number of point charges in a resultant of force due to individual point charges. Therefore, force on a point test charge due to many charges is given by the equation. So this is the equation. F is equal to F1 plus F2 plus F3. So next. So Superposition of forces from two charges. Blue charge pick negative equal charge Q. What is the force of positive charge? So consider effect of each charge separately. So it's the negative and it's the positive. So take each charge in turn. Create a vector sum. And find the result. The net force. So next is the superposition principle. So example, electricity balancing gravity. Two identical balls with mass M and charge Q hang from similar string of length L. After figuring which they find the charge of Q as a function of delta n. Electric potential. The potential is just a scalar function. Electric potential is related to the work done by the external force when it transports a charge slowly from one position to another in an environment containing other charges. The difference between the potential at point A and the potential at point B is defined by the equation. So, the equation is VA minus VB is equal to work of the charge Q from B to A over Q. So dielectric polarization and electric dipole. The amount of charge stored in a capacitor is the gradient of the voltage in the capacitor. What limit of the amount of the charge that can be stored in the capacitor? The voltage can be increased, but the electric breakdown will occur if the electric field inside the capacitor becomes too large. The capacity can be increased by expanding the electrode areas by reducing the gap between electrodes. In general, capacitor can be withstand high voltage have a relatively small capacity. So the capacitor have its limit, and once it overlaps the capacity, it will break down, but it can withstand a high voltage. So if only low voltage are needed, however, compact capacitor with large capacities can be manufactured. One method of increasing capacity is to insert between the conductor and insulating material that reduces the voltage because of its effect on the electric field. Such materials are called dielectric. This is a substance with no free charges. When the molecules of a dielectric are placed in the electric field, their negatively charged electrons separate slightly from their positively charged force. With this operation referred to as polarization, the molecule acquire an electric dipole moment. A cluster of charge with an electric dipole moment is often called an electric dipole. So, is there an electric forces between a charged object and cheap matter such as a piece of wood? Well, yes, and of course it's exactly. The reason is that under the influence of the electric field of charged object, the negatively charged electron and the positively charged nuclei within the atoms and molecules are subjected to force within. So the result is the negative and the positive charge separate themselves each other. Such atom and molecules are said to be polarized and to have an electric dipole moment. The molecule in the wood acquire an electric dipole moment in the direction of the external field. The polarized molecules are attracted toward the charged object because the field increases in the direction of the charged object. The electric dipole moment P of two charges, plus Q and minus Q, separated by the distance 1 is a vector of magnitude P is equal to Q1 with a direction both the negative and positive charge. An electric dipole in an external electric field is subjected to a torque sine delta, where delta is the angle between P and E. The torque tends to align the dipole moment P in the direction of P. The potential energy of dipole is given by U is equal to negative PE cosine delta, or in effect notation, mu is equal to AC multiplied by E. So, in an uniform electric field, the potential energy of an electric dipole also varies with position. When the dipole can be subjected to a force, the force is a dipole in the direction of increasing field when P is around it, since the potential energy UE decreases in that direction. The polarization of a medium P gives the electric dipole moment per unit volume of the material. It is expressed in units of coulomb per meter squared. When a dielectric is placed in an electric field, it's acquire a polarization that depends on the field. The electric susceptibility Xe relates the polarization to the electric field as P is equal to Xe. In general, Xe varies slightly depending on the strength of the electric field, but some materials called linear dielectric, it is constant. The dielectric constant K of a substance is relative to its susceptibility as K is equal to 1 plus Pe over 2 is a dimensionless. So this is a table for the electric constant of a fixed substance. So plastic 1, air 1.006, oil is 2.2, polyethylene is 2.26, beeswax is 2.8, beeswax is 3.78, water is 80, calcium carbonate is 168, and barium chloride is 1250. So the presence of a dielectric affects many electric quantities. A dielectric reduced by a factor K. The value of electric field is a constant E, also the value of the electric potential can be charged within the medium. As seen in the table 1, the dielectric can have a large effect. The insertion of the electric between the electrodes of a capacitor of a given charge reduces the potential difference between the electrodes and thus increases the capacity of the capacitor by the factor K. For a parallel plate capacitor filled with a dielectric, the capacity becomes C is equal to K A over D. A third and important effect of a dielectric is to reduce the speed of electromagnetic waves in a medium. So next, the principle of capacitor. To understand how a charged capacitor stores energy, consider the following charging process with both plates of the capacitor initially uncharged. A small amount of negative charge is removed from the lower plate and placed on the upper plate. Thus, little work is required to make a lower plate slightly positive and the upper plate slightly negative. As the process is repeated, however, it becomes increasingly difficult to transport the same amount of negative charge since the charge is being moved toward a plate that is already negatively charged and away from a plate that is already positively charged. The negative charge of the upper plate repels the negative charge moving toward it, and the positive charge on the lower plate exerts attractive force of the negative charge being away. Therefore, work has to be done to charge the capacitor. So capacitor come in a wide variety of shapes and sizes. Not all have a parallel plate. Some are cylinders with two plates, each 1 square centimeter in area, separated in dielectric with case equal to 2 of 1 millimeter thick. Of the capacity is 1.76 times 10 12 F, about a picofarad charge to 20 volts. The capacitor will store about 40 coulombs of charge. The electric energy stored would be 400 picojoules. Even small capacitor can store enormous amount of charge. Modern techniques and dielectric materials permit the manufacture of capacitor that occupy less than 1 cubic centimeter and yet store 1010 times more charge and electric energy in the above example. So application of the capacitor. Capacitor have many important applications. They are used, for example, in digital circuits so that the information stored in large computer memory is not lost during the momentary electric power failure. The electric energy stored in such capacitor maintains the information during the temporary loss of power. Capacitor play an even more important role as filters to divert spurious electric signals and thereby prevent damage to sensitive components in circuit caused by electric charges. So next is electric field. So when a small positive charge is brought near a large positive charge, it experiences a force directed away from the large charge. If the test charge is far from the large charge, the electrostatic force given by Coulomb's law is smaller than when it is near. This state of direction and magnitude of the electrostatic force due to fixed charge or set of fixed charges constitutes an electrostatic field. The electrostatic field is defined as the force per unit charge exerted on a small positive charge Q placed on that point. So this is the equation. So the rule for drawing electric field lines for any static configuration of charges are the lines begin on positive charge and terminate on negative charges. The number of lines row emerging from the terminating on the charge is proportional to the magnitude of the charge. No two field lines are ever crossed in a charge-free region, and the line approaches the conducting surface perpendicularly. So electric field, this is the representation of an electric field surrounding a positive charge and negative charge. So the green one is the positive and the red one is the negative. These lines are called field lines. Lines or line of force can think of electric forces as establishing field telling particles which way to move on compass. So usually the positive ones move away while the negative ones come what do you call that? They come together. So the following figure will show you the electric field for opposite charge, similar charges and opposite charge. So this is a positive. I told you that the green is positive and the red is the negative. So this field is electric field for opposite charges. So after repelling it from the positive charges, what do you call this? It's approaching the negative charge because the negative charge attracts the positive repel. So this is a electric field of similar charges. So there is two protons, and as you can see, they are repelling to each other. So this is a oppositely charged plate, and the the proton is being attracted to the electron. So electric flux. Electric flux is defined as the number of field lines that pass through a given surface. In the figure, line of electric flux emerging from point charge pass through the imaginary spherical surface with the charge itself. So electric flux, this is the definition expressed the following. So this is the equation where phi is the electric flux and E is the electric field and A is the perpendicular of the field lines. Electric flux is measured by this equation. So in general terms, flux is close general to the dot product of electric field vector and the vector A, and the direction of A is outward, normal to the imaginary surface. Mathematically, electric flux is accepted by the convention that is in flux lines are positive if leaving the surface and negative if entering the surface. So Gauss's law provides a method to calculate any electric field. However, its only practical use is for fields of highly symmetrical distribution of fixed charges. The law states that the net electric flux to any real or imaginary closed surface is equal to the net electric charge. And flows within that the surface divided As the result, if no charge exists with a given closed surface, there is as many flux lines entering the surface as there are leaving it. The imaginary surface is carried on several planes for the Gaussian is for calculus. So wherein delta is the angle between the direction and is the outward direction of normal to the surface. Please permittedly constant. Consider that calculation of the electric field due to a point charge figures the direction speed in the Gaussian surface because the electric field is perpendicular to the Gaussian surface and directed outward 0 to 90 degrees and cosine delta is equal to 1. Substitute in the area of a sphere and let it the side reduces to this or this, which is the same expression obtained from Coulomb's law and the definition of electric field in terms of force. The derivation of the expression for the field due to thin conducting shell of a charged ball shows the electric field for A and shell radius R, B and the Gaussian surface for outside the shell, and C the Gaussian surface and D inside of the shell of the radius. So when the shell of charge as in figure A, this figure, the left side of Gauss equation which is the following expression from the same reason given from a point charge. Therefore, this equation thus the electric outside the field space charge is the same as if the same amount of charge were concentrated in a point located at the center of the sphere. The Gaussian surface inside the sphere enclosed to no charge, and therefore there is no electric field inside the uniformly charged spherical shell. The same truth holds within a solid conductor because all of the charge of the conductor resides on the surface. Because the electric field inside even an irregularly shaped conductor is zero, the change will not be evenly distributed over a regular shape. The change will tend to accumulate on protruding points on the outside of the conductor. So potential difference and equipotential surface. In the preceding example, the charge distribution were spherical and so the Gaussian surface were a sphere. When finding the electric field of either a sheet of charge or a line of charge, the cylinder is correct. Gaussian surface electric field for a non-conducting sheet of charge. The electric field is directed towards the shape opposite it. The charge per unit is sigma. So this is the Gaussian cylinder. Wherein the area of a closed cylinder Gaussian surface will be the sum of the areas of the left end and the right end of the wall. Therefore, summation of EA cosine delta is equal to EA cosine delta left end plus EA cosine delta right end plus EA cosine delta wall. The electric field is a parallel to the wall which is at right angle of the outward normal of the area. Thus the last term on the right is zero at each end. E is the same direction as the outward normal, so EA cosine delta left end plus EA cosine delta right end is equal to 2EA, where A is the area of the end of the Gaussian cylinder. The total charge inside the Gaussian surface of the product can be get by using this equation and this equation. So the resultant of electric field of two parallel plates is global that one shift with the same charge using this and this or this, where Q is the charge of each plate and A is the area of each plate. If the plates have opposite charges, the electric field will exist between the plate and be zero outside the plate. If the charges are equal to sign, The electric field will be zero between the plates and expressed by the above equation also the plates. This result can be derived by Gauss